We'll first set up a graph convolutional network to perform node classification. This classification model will run using the node's features and also use the inner connections that exist in the graph. That is the citation links between scientific publications to determine what class or category every scientific publication belongs to. This graph convolutional network will serve as our baseline classification model, and we'll see how a graph attention network improves upon this model in the later part of this demo. Let's set up our GCN first. We know that a graph convolutional network works by aggregating and transforming features from a node's neighbors in a graph, applying a neural network to learn node representation. And each node's embedding, so the node representation, is updated iteratively by combining information from the local graph structure. The GCM class defined on line 5 sets up our graph convolutional network. Now, the init method takes in a number of input arguments, the number of channels in the input, the number of channels in the output, and the hidden dimensions for our graph convolutional network layers. Those other hidden channels set to 16 by default. The input channels represent the number of features for each node. The output channels correspond to the number of classes or categories into which an individual node can be categorized. On lines 11 and 12, we instantiate two GCN conv layers in our graph neural network. In channels for the first layer is equal to the input channels, number of node features. Out channels is equal to hidden channels. For the second convolutional layer, in channels is equal to hidden channels and out channels is equal to output channels. That is the number of classes or categories. The forward method defines a forward pass through the graph neural network. From the data passed in, we access the feature matrix X and the edge index. That is the connection between nodes. And we pass those through the first convolutional layer. That's on line 17. We then pass the output of this convolutional layer through the ReLU activation function. On line 20, we use a dropout layer with a dropout percentage of 50% to mitigate overfitting on the training data. And we pass the output through the second convolutional layer. And that is the output of the forward pass through the neural network. Our graph convolution network here is fairly straightforward. All of the heavy listing is done by the GCN conv layers. Because we have two layers in our neural network for each target node, the local neighborhood information from nodes to hop survey will be included. Let's get set up with the data to train this convolutional network. The device that we'll be using will be a CUDA device. Because we've enabled GPUs access the Corad graph, input channels is equal to num features, output channels is equal to num classes. Next, we instantiate the graph convolutional network that we've just defined with the input channels and the output channels and move the model's parameters to our CUDA device. I print out the model and compute the number of parameters that we are going to be training. Here, you can see that we have about 23,000 parameters that we need to train. We'll set up a utility method to visualize the classes or categories to which the nodes belong. We'll use the t-SNE dimensionality reduction algorithm to view the distribution of the graph nodes and the corresponding classes or categories in two-dimensional space. The visualize function here takes an H. That is the predictions from our model across the 7 classes or categories and the color for the individual classes or categories. On line 5, we use t-SNE or the t-distributed stochastic neighbor embedding dimensionality reduction technique. To visualize this high-dimensional data, t-SNE projects data points onto a lower dimensional space, and we've reduced dimensionality down to 2 dimensions and components equal to 2. And then we view a scatter plot representations in 2 dimension of the graph classes or categories. In order to show you how this utility function works, let's use it. Now, our graph hasn't been trained, so the output of this graph neural network is going to be completely random. We pass the graph through the model, and the output of the model be passed to the visualize function to visualize the classes or categories into which the individual nodes have been classified. And you can see here from the different colors, there is no clear order or grouping to the colors, indicating that the categorization is completely random to start off with. Once we have a trained model, you'll see that publications that belong to the same category will be clustered closer together in space.